So at the start of this recording, there are not a lot of Graylog resources out there on YouTube, so it might be a little silly, but I thought I'd read through the documentation, take my notes like I usually do on my own, but then share it to people through this video. So you can go to docs.graylog.org, and at the very beginning here, they're going to talk about architectural considerations. There are a few rules of thumb when scaling resources for Graylog. Graylog server nodes should have a focus on CPU power. These also serve the user interface to the browser. So a node serves the user interface to the browser. Elasticsearch nodes should have as much RAM as possible in the fastest disks you can get. Everything depends on I/O speed here. MongoDB is storing metadata or meta information and configuration data and doesn't need many resources. And if you haven't stood up your own Graylog server, Elasticsearch and MongoDB is supposed to be installed along with it. Maybe if I create another one of these on a VM, I'll go ahead and show everybody, or I'll create a video to show you how, because the other videos out there are not too good. With the exception of IT Security Labs here, this guy does a wonderful job. I just needed more help with the inputs at the end of that installation process. So they say, also keep in mind that ingested messages are only stored in Elasticsearch. If you have data loss in the Elasticsearch cluster, the messages are gone, except if you have created backups of the indices. So 2 questions based on the first section here. What are ingested messages? Where are ingested messages stored? They're only stored in Elasticsearch, and how bad would losing Elasticsearch cluster be? Horrible unless you have backups of the indices. Here they're talking about the minimum setup. Graylog could be used for smaller non-critical or test setups. None of the components are redundant, and they are easy and quick to set up. So you have your devices and applications log messages in this little cloud here. Goes to Graylog, which works with MongoDB and Elasticsearch, and then can send that information to you via the browser. Our virtual machine appliances are using this design by default, deploying nginx as front-end proxy. And there's more information about that, but I'm going to try to stay linear here. For a bigger production setup, for these environments, you can have several Graylog nodes behind a load balancer distributing the processing load. The load balancer can ping the Graylog nodes via HTTP on the Graylog REST API to check if they are alive and take dead nodes out of the cluster. So here's our diagram. Here they said HTTP, but we see you could do HTTPS. Here they have this red arrow, syslog, gilf, beats. Red for beats, right? Just kidding. So this goes to the load balancer, which then looks for availability. Basically, we're looking at multiple servers here, working with another set of multiple servers. Pretty straightforward diagram. In terms of planning and configuring such a setup, we'll be reading this part, a multi-node setup guide, and then some guides on the Graylog Marketplace also offer some ideas how you can use RabbitMQ. I actually really like that. Went to a training on Rabbit. But you can use Rabbit or Apache Kafka, to add some queuing to your setup. If you're really interested in the Graylog architecture at a more detailed level, which I love details, I love low level, whether you want to understand more for planning your architecture design, performance tuning, or just because you love stuff like that, our cheeky engineering team has put together this deep architecture guide. It's not for the faint at heart, but we hope you love it. Alright, and it looks like it's a slideshow. But yeah, since the next section is getting started, let's go through that slideshow. There's only 13 of them. So the README. This is not a guide for the squeamish. This is a peek for those who like to go off the beaten path, sometimes alone, for those who aren't afraid of pulling open the hood and getting their hands dirty. This is the culmination of 5 years of engineering design in our hope to bring you the fastest machine data processing engine on the planet. There we go. Much easier to see. And I'm just going to take down that quote because it sounds like a great goal. So here's a pretty picture my 5-year-old drew. Just kidding. Over here we have log messages and load balancer. 2, load balancer. 3, transport layer. 4 is over here, the processing chain. Then 4.5 right here is the REST API. Number 5 goes over here, MongoDB. 6, Elasticsearch cluster. 7 is the anatomy of a single index. 8 is the index model. And then Deflector queue. Sounds like something off Star Trek. So the TLDR here is basically send us any machine data, structured or not, and use whatever load balancer you like. The number of messages, their peak rates, average size, and extractions performed will affect performance, but we'll cover that later. The transport layer. This is the inputs and journal on top of the Graylog server. It consists of inputs from the message cloud. This is our syslog stream, as well as other inputs. So what's another name for syslog stream? These, I assume they're talking about inputs. So these inputs get pre-processed without user configurability into parts of a message. While the journal is on disk I/O, it is an append-only journal where there's no seek time. Internally, we reuse Apache Kafka code to do this, thanks LinkedIn. The write needle is always close to the same point on the disk, so it does not constantly scan. This makes it blazing fast. You can turn it off, but we do not recommend it. And then the last paragraph, why we did this. Other systems do not have this, so they will lose messages coming in when message spikes happen, because the network layer will start to reject them, or your local memory will explode. So I hope I accurately summarize these 2 paragraphs here in a question and answer format. What's not clear to a newbie like me is I'm wondering if all the inputs are getting just straight put on disk. Granted, in this, pre-processed, append-only type of format. And though it's great not to lose messages, are we ever looking at a problem where the disk gets full? And then, I don't know, what happens after that? I know this is only video 1 of a long series on Graylog documentation, so the answers might come later. So to talk about the processing chain, these messages are then taken and written into a process buffer, which is a ring buffer. We are using the Disruptor library from LMAX, a high-speed trading company that relies on high speed and low latency. Now messages are then processed by the process buffer processor, where stream routing and extracting of fields happen. This part can get CPU intensive. The filtered message then goes into the output buffer, another ring buffer, and then the output buffer processor, and onwards to Elasticsearch or user-defined output. So after reading that, my genuine question is, what is stream routing? I need to wrap my mind around that a little bit better. Other than that, though, I feel pretty good about the idea of certain fields being extracted then sent to Elasticsearch. Now, a pro tip, they say, is tuning the number of processors run per buffer is important and should never exceed the number of CPU cores you have available for Graylog server. Increase number of processors if you see too low throughput, and try to focus on buffer processors because the output buffer usually does not need many. A symptom of not enough processors is full buffers. Alright, so that's some good information. I might need to play around with that a little bit to really internalize the information. For REST API, why is this different than any other REST API? Well, this is the same API we use on our web front end, hence you can make any read-write call we do in your own UI. Yep, you can build your own front end. Also, it has to be high quality. Because this is the same API we use ourselves day to day, it is not like others where it is just an API that is provided for external users to integrate with. Built once and patched with duct tape every release. Note that not that we don't like duct tape. So my poor reading probably made that less funny. Let's talk about Mongo now, which is storing only metadata, users, settings, and configuration data on all items. So streams, dashboards, extractors, anything you configure. So if Mongo goes down, Graylog will continue to run. So it is your choice whether to include it in a high availability design. Mongo recommends for high availability scenarios 3 instances of it. This is because if one goes down, the Mongo then Mongo has to recommend a primary, and without two more, it can get confused between the first two. So see Mongo replication set for instructions. Alright, so that's simple enough. Just want to make this a little smaller in case you want to read my notes there. We connect to ES servers as an embedded ES node that does not store data. So we look and act like an ES node and know about configuration data, indexes, shards, etc. for each ES server. Now, when writing to ES and when you are not a node, you have encode and transmit over the wire. When writing to ES and when you are not a node, you have encode and transmit over the wire as HTTP and then JSON and then decode it. That sentence was a wreck. As a node, you can send it in native. Alright, so the TLDR is you want to be an ES node. Graylog wants to be an ES node. So for high availability, we recommend having at least one replica configured. For anatomy of an index, a single index, in this example Graylog index number 25, it is broken into shards. This means the index is broken up and the parts are run on different ES nodes. This makes for faster searches because the query result can be computed on multiple ES nodes in parallel. An index can also have replicas configured. This means that each shard is mirrored to other nodes, which is great for high availability. So that's good to remember what shards are good for. Next up, index model. Each index is numbered starting with 0 the first time. In a time series database, all data is stored with a timestamp, and once it is stored, it is not gone back to be rewritten, hence is marked as read-only or write active for performance. So messages are not gone back to be reinserted. This makes it fast because of the time-based storage. This also means when you query it, you must give a time-bound search. Pro tip, so the size of these indexes matter when performance tuning. You don't want to make the indexes too big because then the searches would take much longer, and you don't want them too short for the same reason. The indexes should be sized based on the amount of data you have and how far you normally search. Sometimes people use it for longer historical strategic type searches. It is important to know and size this correctly. So which question should you ask when designing an index model? And I should maybe make that plural. So first question, so how much data do I have? How far back do I normally search? The answers to these questions will determine the size you make your indexes, which, don't forget, are then sharded. Number 9 is Deflector. We write to an index alias called Deflector. This allows us not to worry about having to stop message processing when creating a new index because that is error-prone to manage. Oh, index number 25 is now closed. Oh, wait, okay, the next one is 26. Go ahead and write. So why are we telling you this? Because, well, it's these kinds of things that make us different. We are proud of thinking about all the small things that give you a great deal of performance and stability, and hope you have enjoyed reading this as much as we did writing it. So, very hilarious picture. Is this their development environment? Looks like a pretty good time. So with that said, I hope this was a good first video all about the architectural considerations. In the next one, we'll actually get started.